Hey everyone, today we are going to solve the readable question by Sudoku. Okay, so let me explain with this example. All numbers should be unique in each row, each column, and each box, right? So to do that, so it's good idea to have rows and columns. And boxes. So every time we find a new number, so we should add that number to rows, columns, and boxes. So let's see one by one. So first of all, at row 0 doesn't have, and duplicate 3 is 1. So this place should be row 0 and column 4. And check if we have 7 at row 0, but we only have 5, 3. So that's why add 7 to row 0. And how about the column? So we don't have data at 7 column. 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 So we don't have data at
And welcome back, and let's write some more neat code today. So today let's solve the problem valid Sudoku, and I'm going to be recording write some more neat code today. So today let's solve the problem valid Sudoku, and I'm recording this on the 4th of July, so hopefully there aren't too many firework noises in the background. So we are given a 9x9 Sudoku board, and all we want to do is determine if the board in its current state is valid or not. And they tell us only the filled in cells need to be validated according to the 3 rules of Sudoku. So basically, each row must only contain digits between 1 through 9 without repetition. The same is true for every single column in this board. It can only contain digits 1 through 9 without repetition. That means we can't have duplicates in any particular row or any particular column. And the third part, which is going to be the most tricky, is each 3x3 sub box. Basically, you can kind of see it in the drawing, right? This entire 9x9 grid is made up of 9 3x3 grids, right? There's one here, one here, one here, and basically 9 of them, as you can see. So basically for each of these 3x3 subgrids, we also want to check that it only contains digits 1 through 9 without repetition. Basically without repetition, that means it has to contain every single digit from 1 through 9. Now of course the Sudoku board doesn't necessarily have to be filled in. You can see this 3x3 is not filled in. But in this case, we are going to say, okay, this one is valid because it only has a 6 and it doesn't have any duplicates, right? But we don't only have to check each 3x3 grid, we also have to check every single column and every single row. Now, before I get into the solution, let me just very quickly clarify what this problem wants from us. You might overcomplicate it and think something like this. What if we had a row such as this one? It has 1, 2, 3, 4, 5, 6, 7, 8. That must mean, even though this spot is empty, that must mean a 9 has to go here, right? That's pretty obvious. But take a look at this column. It has 2, 3, 4, 5, 6, 7, 8, 9. That must mean that the value that goes here has to be a 1. So we have a contradiction. We have to either put a 1 or a 9, but we know that both need to be in this position. So in this case, this is not a valid Sudoku board, right? Well, that's technically true, but for this problem, we are going to consider this board, yes, it's valid, because as of right now, based on what the cells are filled in, like what cells are filled in, there aren't any contradictions. We're not going to assume anything for any of these empty positions, even though we know for sure, yes, a 9 would have to go here based on this row. We're not going to assume that. So it's actually a little bit easier than you might think. So the algorithm is going to be pretty standard, right? We're going to go through every single row and make sure every particular row does not have any duplicates. How could we do that? We could do that a bunch of different ways, but I'm going to do a hash set, right? So a hash set will be easy for us to detect if there are any duplicates. So we're going to have a unique hash set for every single row in the entire grid, right? So then we can easily determine if any particular row has any filled in duplicates, right? This row obviously doesn't. A 5, a 3, and a 7, no duplicates, right? So that portion is pretty easy, right? Number 1 is pretty easy to check. What about number 2, checking each column? We can do the exact same thing. Just have a hash set for every single column, right? Every single column has a hash set, and then we can determine if there are any duplicates or not, right? And for adding an element to the hash set is O of 1, checking duplicates is also O of 1. So far we have a time complexity. If we're just checking the columns and the rows, we have a time complexity, which is basically the size of the entire grid, which is 9 squared pretty much. Now the last part, in theory, should also be pretty easy, but coding it up is a little bit more tricky. There are many ways to do it. I'm going to show you the easiest way. We want to be able to tell, okay, for every 3x3 grid, which there are 9 of, does any of them have any duplicates? So again, we can use a hash set to represent each of these 3x3 grids. But the question is, how are we going to do it? How can it be easy to code something like that? And that's what I'm going to quickly explain to you right now. And after I do, we can jump into the code. The overall solution is yes, though, going to be O of n 9 squared. We're pretty much just going to have to iterate over the entire grid and nothing else. But we are going to have extra space, also O of 9 squared, because we're going to have 3 hash sets, which are going to be this exact size. So roughly, this is the memory complexity as well. So we want to represent each of these 3x3 grids with a hash set. But how do we know if we're at any particular value, right? Like I have labeled the indices, right? This is going to represent what row, this is going to represent which column. How do we know if any particular value, such as 1, 1 happens to be, we have 9 different subsquares. We have 9 different subsquares. We're going to have indices to represent them, right? A 1, 1 means that this is the subsquare that we're talking about, right? This one. And the way the math is going to work out is, since each of these is 3x3, we can just take the actual index, such as 4. Let's say we were given 4, 4, right? This is the square we're talking about. We can take 4, which is the row, divide it by 3, integer division, right? We're talking about integer division. 4 divided by 3 is going to give us a 1. Similarly, we do the same thing with the column, right? 4 divided by 3 is going to give us a 1, right? So if we take the actual coordinates 4, 4, divide the coordinates integer division by 3, then we get the index for the row column. It basically identifies which square this is a part of. Now let's just check that the edge cases work out. Let's try 8, 8, right? This is the boundary. What happens if we take 8 divided by 3 and 8 divided by 3, right? Well, then we get 2, 2, right? Integer division, we always round down 2, 2. That works out for us, right? Let's do a different edge case. Maybe we try this square, right, on the boundary. Does this identify 0, 0? Because that's what it should. Well, let's take the positions, the indices, 2, 2, divide them by 3, 2 divided by 3, 2 divided by 3. We round these down, so we get 0, 0. That does uniquely identify, or correctly identifies that it belongs to this 3 by 3 grid. So that's kind of how we're going to identify when we go through every position, every cell in the entire Sudoku board, which of the 3 by 3 grids is it a part of, and then we can add them to that, right? So we're going to have a hash set where the key of the hash set is going to be a pair of values, the row column, not the actual row column, right? But when we convert it to the row column, basically row divided by 3 and column divided by 3. That's what the key of the hash map is going to be. And the value is similarly going to be a hash set where we can tell, do we have any duplicates in this 3 by 3 grid or not, right? Same for every single 3 by 3 grid. We're just checking, does it have any duplicates? If not, then we can continue. If it does have a duplicate, that means our Sudoku board is not valid, and then we would have to return false. But if it is valid, we're just going to continue. So we're basically going to go over the entire grid, right? Every single position in the entire grid. If we find any duplicates, we return false. If we don't, at the end, we can return true. So now we have enough information to actually write out the code. So let's do that. Okay, so now we can write the code. Like I mentioned, I'm going to be detecting duplicates with a hash set, but you could do it with arrays if you wanted to as well, because we know the dimensions of this Sudoku board. It's 9 by 9, but I'm going to be using a hash set or dictionary just because it's easier. So in this case, column number values only for the squares is going to be a pair of values, basically the row divided by 3. And the column divided by 3. So now we just want to iterate over the entire grid. And we know the dimensions are 9 by 9, so I'm just going to hard code that in to these loops. And so we know that a position in the Sudoku board actually could be empty. Check in next iteration we have, then we return, it has it all row. What does it then? So that's a set of all. So basically, if this can return false, but that's not it. Basically, a column that we're at, we have 4. So how do we get the current for that column divided by 3? So that tells us above of this value set current Sudoku board. So we're going to do the key. So this makes sure that our hash sets are updated. Any dupe with is pretty efficient.
Hey guys, Greg here. Let's solve best time to buy and sell stock, lead code number of a given stock on the ith day. And you want to maximize your profit day in the you can achieve from any money. Okay, so if you get this array of prices here, 715. So if one here, okay, well, you can't sell it at 7 and make 6 profit, because if you bought it here, this day has already passed. You can't sell it over here. But if you buy it here, you could sell it here to make 4, or if you bought it here, you could sell it here to make 2, or most importantly, if you bought it here, you could sell it here to make a profit of 6 minus 1, which is 5. And the max amount of profit you could get is that, which is 5. Now, before we worry about an optimized solution here, we can come up with the brute force pretty easily. You just need to look at all possible pairs of days. So x would try and find of negative infinity in the range of the length of the profit. So I is your buying till the end. Minus that profit is greater than 0, then you want to set profit. You only want to set these negative infinity, basically meaning that you did not find any profit. So we'll return max profit if the max profit, meaning we didn't find any profit. So we can run that, and that is going to work. However, that's not going to pass our test cases because this has a time complexity of big O of n squared. Because we have a nested for loop, we look at all of the days we could buy it and then all of the later days that we could sell it. So that is a time of O of n squared. Luckily, it does have a space of O of 1, which is nice. However, we can do a lot better than that. So let's go visualize a better solution. Now, the idea is to keep track of two different variables. We'll call one max profit, basically the exact same thing we just saw with the previous max profit. And it's actually a little easier just to set this to 0 than to infinity. Therefore, it has a default at 0. And the other thing you'd be interested in is the minimum price that we've seen so far. So we'll just call that minimum price, and we're going to set that just to infinity. Then we're going to iterate over the array and see that we have a price of 7. Is that a better price than our min price? We're currently at infinity, so 7 is a lot better. So the next one here, we see 1. Is that a smaller minimum price? Yes, it is. And so we're going to mark that as 1. Over here at 5, that is not our minimum price. If our current price is 5, and we've already previously seen the minimum price of 1, well, then we could actually get the profit of 4. And so that profit of 4 is better than the max profit we've seen so far, which is nothing. So we should update that to be 4. Now, when we look at the next number, we see 3. Okay, well, we could buy it at 1 and sell it at 3. So that would be 3 minus 1, which is equal to 2 in profit. Well, that's not better than our max profit, so we're not going to use that one. We move over and see 6. Okay, we could buy it at 1 and sell it at 6. So 6 minus 1 is equal to 5. That is a better max profit, and so we would mark this as a 5. And when we get to the final value here, buying it at 1 and selling it at 4, so 4 4 minus 1 is equal to 3. That's not any better, so we'd return 5. The algorithm is pretty simple. We just keep track of the minimum price we've seen and try to see if we can come up with store and infinity, currently profit. If the potential profit is equal to the current value we've seen and the max profit to it, you would return the max profit at the end. And if you're